So basically, I'll be talking about the like basically the same topic, topological phases, but I want to add higher symmetries to them. And my talk will be based on the recent two works with collaborators Wen, Kong, Zheng, and Zhang. And before we really start, I want to say, like, as a last speaker, actually my talk is more like a blueprint for the framework of topological phases with higher symmetry. And from a mathematical point of view, many contents should be regarded as conjectures. And the main idea is actually similar to that has been mentioned many times in the previous talks. We want to describe topological phases by here fusion categories with trivial center. But now, since we have symmetry, this trivial is not completely trivial. This is trivial relative to some given higher symmetry. So because of this is trivial relative to symmetry, we have some non-trivial structures that we need to address. Okay, so the first thing I want to do is give a proper definition for this higher symmetry. And let's begin with a flat reflection of what we know in Euro quantum system. So when we see a quantum system is described by a Hamiltonian H and a Hilbert space V, when we see it has some symmetry, we really mean there's a group. It acts on the Hilbert space. Let me, yeah, it was a spotlight. Okay, so the group acts on the Hilbert space. And the action commutes with the Hamiltonian of the system. But this is just
slide is not updated on the screen, on my screen at least. Still the title page.
Maybe my connection is not very good. Is it okay now?
No, it's still title page.
Yeah, it's still the first page.
Oh yeah, now it
Okay.
comes. Yes. Okay.
I'm sorry. So let me repeat. If we are considering some symmetry, Euro global symmetry in a quantum system, we mean that's a group with action on the Hilbert space, and the action commutes with Hamiltonian for any group element. So this is just a roughly speaking what is symmetry, but in physical application, Euro physics really not mean some specific quantum system with some specific Hamiltonian. Physics, what is in physics mind is really some generic Hamiltonian, generic system. And in particular, we would allow any symmetric perturbations, and we want to like have a series of quantum systems that we can take the thermodynamic limit to define a phase. So more precisely speaking, we should consider a class of Hilbert space with the group action and all possible Hamiltonians that commutes with the J action. So we can just make things easier. This just means we are really working in the category of group representations. So we just take all the group representations and consider our quantum theory inside this category, whose objects are this vector space with action, and morphism are the intertwiners or symmetric operators that commute with J action. So basically, we can say if there is no symmetry, we just work in the category of vector space. That's where quantum mechanics lives in. And if there is symmetry, we upgrade the category we are working from vector space to group representations. And there is a famous duality, is a Topological duality that relates the group to the categorical description. So basically, the categorical description is the permutations or symmetry charges or conserved quantities. There are some invariants, physical macroscopic observables. And if you supply a fiber functor here, in this case, just forget the functor from revg to vec, then you can reconstruct the symmetry group by taking the automorphism of the fiber functor. And these two, they are just equivalent descriptions of symmetry. And the communication relation between the group actions and the symmetric operators, such as Hamiltonian, is naturally encoded in the definition of the natural transformation. And I draw the computed diagram here. If you take any group element in the automorphism, it is a natural transformation, and its component on the representation is just the corresponding group representation, group action. And it commutes with symmetric operator from V to V prime. And to generalize this idea, we want to give this Thematic formalism a more physical interpretation. We, as I already explained, we can consider this revg as the systems with symmetry. And the categorical space are the systems with no symmetry. And forget functor here is just a process of symmetry breaking. So that's the basic idea. I want to really define the generalized symmetry in terms of this Thematic formalism data, but maybe in some different category, in some different category of physical series that we're interested. But the interpretation is the same. We still take R as the series with symmetry and some V as a trivial series without symmetry. And we need to pick some symmetry breaking morphism in this appropriate category. And if you have like enough nice properties of this data, you'll be able to reconstruct the symmetry algebra by Topological duality. Let's take the endomorphism of beta. Okay, so the category we are interested now is a category for topological phases. And I think after this workshop, this many talks, we should almost agree a good choice would be the category of fusion in categories. So then we arrived at this definition of higher symmetry. We need to pick some V for V is a fusion category, and it is physically the so-called the elementary excitations. And for example, it can be boson fermions, but I will explain this in more detail later. So our definition for a higher symmetry is basically a fusion in category, denoted R, together with a monoidal functor from beta to the V of your choice. And this beta, we want it to be surjective, and and injective on the enmorphism or the operators. And in our paper, we call this structure a V local fusion in category. And in this talk, I will just refer to this data R, beta, and V as a higher symmetry. Okay, so the examples. So V, as I already mentioned, it is the fusion in category of elementary local excitations. And so the trivial example of V, you can take V to be the vector spaces, maybe iterated defined by this looping and continuous completion. So this is for boson system. And there are two typical examples. One is the enriched G. It's already appeared in the previous talks. It means the symmetry charges of a group G and all the higher dimensional condensation defects from the symmetry charges. And for this case, we take beta to be the functor that forgets the group action. So this is basically how we describe zero or global symmetry in this generalized definition. And also, another example is the category of G-graded n-vector spaces. And physically, it is the symmetry domain walls in a spontaneous G-symmetry breaking phase. And it should be the dual symmetry as appeared in the Xiaogang's mini course. So it is the like G superscript n-1 that due to G. And in this case, beta just forgets grading. This is referred to by Xiaogang as the algebraic Hamming symmetry, because if you really apply technical duality here, you will get some kind of higher Hopf algebra that is not a higher group. And this for boson system, and there are of course possibly other examples. For fermion system, we should take V to be the higher supervector space. And similarly, we can define zero fermionic symmetry and also others. And this fermion system, this fermion case, and this dual symmetry of zero form symmetry, they are basically the two things that force us to generalize the notion of symmetry to such a stage. But after we're doing this, actually we can consider something more exotic. You can take some more exotic V that is neither vector space or supervector space, and possibly they mean you have a system that fundamentally built with anyons or strings or other higher excitations. And my goal is not to spend too much effort on these examples, but I want to tell you the general framework to treat all the kind of symmetries on an equal footing. Okay. Is there any questions? Okay, let me move on. So now I want to define n+1 dimensional topological phase with given higher symmetry. But remember, if you the category description is just a collection of macroscopic observables, and in fact, no matter there is symmetry or not, this n+1 dimensional topological phase, so all the excitations in there and defects, they should always form a fusion in category. And by the term with given symmetry, it physically should means you can really measure the macroscope observables of the higher symmetry, which is in this case just the category R. So, so we begin our definition as partial by requiring embedding. So here, first you want to have a fusion category C that for the observables in this topological phase, and then you want to have an embedding from the given symmetry to the category of the topological phase. And here embedding we mean something that's equivalent to this image, but because it's higher thing is hard to define it precisely. Okay. So the next thing we want to do is compute the bulk. There are some missing data hidden in the bulk. And the basic idea is that anomaly free, if the topological phase is anomaly free, it implies it is equivalent to having a trivial bulk. And the bulk is mathematically the center. So we need to formulate a proper notion of center that is relative to the given higher symmetry. And our working conjecture is we just take the E1 center. It is the bimodule into function, and we add some additional structures that is relevant to the higher symmetry. So, so to begin with, we consider the trivial phase. What is a trivial bulk? It must be the bulk of the trivial phase, and the trivial phase should be, so at least this embedding is at least is identity functor. So for trivial phase we have C equals to R, and then the bulk of R should be somehow trivial. Then comes the question. So the bulk of R, ZR, we see it is trivial, but it's not completely trivial. So when we see some hierarchy phase, its center is the same as the trivial phase, the trivial bulk, we need to characterize in the higher structures. And in this talk, I will mainly discuss this top level equivalence braided functor from the center of R to the center of C. And higher structures are basically open problems, but I will touch them a little bit. And besides this equivalence, the structure, the data, we also need some conditions. We need to formulate how the additional structure of symmetry is preserved by this equivalence. Okay, so let's first look at the special case. We assume for the moment that our higher symmetry, this R, is a symmetric fusion category, or what we call a braided fusion category. In this case, we have a canonical embedding that we can embed R into its bulk. It's braided embedding. So basically, you use the braiding of R, and it just put them as the braiding in the half braiding in the dream field center. So we think this data, this canonical embedding, is additional data of the symmetry. It describes a trivial phase, a trivial bulk with symmetry. And if R is actually symmetric, this is already mentioned in the, I think, in Tian's talk. This DR is just the minimum normalization of R. It is trivial in the sense it's described the trivial topological phase, trivial phase with symmetry, or trivial SPE phase. So besides this canonical embedding, we also have this canonical forgetful functor from the center to C itself, from boundary to from bulk to boundary. So we immediately arrive at a very natural formulation. We just put things together. So this definition for symmetric R. If R is symmetric, then anomaly free and plus one dimensional higher SD phase with this R symmetry is characterized by the following three data. First, fusion category C of the observables, macroscopic observables, embedding that embeds the symmetry into C, and also a braided equivalence between the bulk. And if you first lift R into the bulk and apply this equivalence and forget, it should coincide with the embedding in this second data. Okay, so that's basically the definition, and spend a slides to briefly discuss the higher structures. it can be very complicated, and I just illustrated like the first level. If you have like an equivalent SET, and I use this C prime. So the inner square is our definition in the previous slide, and the larger square with everything with prime is something equivalent to C. So if you want to really connect them, you need, for example, a monoidal equivalence between C and C prime, and this monoidal equivalence lift to the center. It induces a braided equivalence in the center, and also you should fill like these two cells with some natural isomorphisms, and you can also imagine there should be some modification or higher cells in this whole three cells, and if you actually you need to iterate this on and on until the operator's top level. So basically, this is the thing we have not touched in the paper right now, and it's an open problem. But really, if we really want to count the SETs, we need to mod up to those higher structures. So it's still important. Okay, and as a special case, we can talk about the higher symmetry protected phases. And by symmetry protected phase, we mean this phase is not topological. There is no topological citations, so all the SPD phases have C equals to R. And then our definition reduced to this diagram, just autoequivalence of ZR that commutes with the canonical embedding. And we can really do this computation in 1+1 dimension, and the result is as this: all the autoequivalence is prism's embedding is just Picard group. For both boson and fermion, it is Picard group. But if you want to further expel that out, for boson, it's just a second group homology group. And for fermion, depends on if this fermion parity is a direct segment or not. You can have an actual Mariner layer contributes as Z2 classification. For higher dimensional things, is still hard to compute for the moment, but we conjecture that it should agree with what we know from other approaches. So if you take R to be 2 rep G, that is the 2+1 dimensional bosonic case, and we conjecture that this thing should agree with the Picard 2 rep G, and also the third cohomology group. And if we take it will be the 2 supervector space, and it should give you this 16-fold weight classification. Okay.
So in this Z16, excuse me, in this Z16, what's the actual symmetry?
It's just the fermion parity.
Just the fermion parity, I see.
Yeah. So it's basically with R is 2 supervect, and V is 2 supervect, and beta is identity. But this, so for I think I didn't mention, but for symmetric fusion category, probably you always have like a minimal symmetric category that you can maps to. Okay. So next, I want to go to the more general case. I no longer want to assume that this R is braided. And the example is this G-graded in vector space, a kind of dual symmetry. And if the group is non-abelian, then it cannot be a braided fusion category. In this case, we no longer have this embedding. And the question comes, how do we characterize, how do we consider the symmetry in the bulk? And the idea is basically, I can translate this functor, monoidal functor, into an algebra, commutative algebra in the center. And this idea dates back to Bluegill and Natalie in this paper. If you have this for fusion 1 category, you have 2 fusion 1 categories and a monoidal functor between them, and assume this F has a red adjoint, then you can take the tensor unit, the image of tensor unit under the red adjoint. It will have a natural structure of half grading, and so leaves bulk, and a natural structure of commutative algebra. Also, if you also this D can be reconstructed. It's equivalent to the category of A modules in C, because here A is commutative. So this A module in C is has a monoidal structure, and this functor F will coincide with the free module functor from C to A mod. It's kind of like a dual version of Tanaka duality. And what we want to generalize this idea to higher dimension as well. So just of course, just a conjecture. We hope that is always true for higher categories. So you have, our definition of higher symmetry is just this monoidal functor beta, and it should determine the commutative, possibly higher algebra in some proper sense. So I'll denote this algebra A beta, induced from beta. It is in the center of R. And we should also have this V equivalent to the A beta modules. And beta is just the free module functor. So physically speaking, this A beta is just something to condense. If you condense A beta, you break the symmetry. That's basically beta is the symmetry breaking process, and A beta is the thing you condense. So the simple example, if you take the Euro zero symmetry in one, no matter what dimension. So rep G, if you forget that two vector, so the endomorphism of this Categorical functor is a group algebra, and the induced algebra is just the functions on G, and it's actually the dual algebra. In this case, this dual algebra contains every irreducible reputations. So in general, we can also think this A beta as some dual algebra to the symmetry algebra. Because of this like rather canonical correspondence, we like replace this embedding for this dual algebra and use this dual algebra as the data as an additional structure for the trivial bulk with symmetry. Okay, and the formulation is also very straightforward. So the n+1 higher SD phase with given higher symmetry. Again, the first two data are the same: a fusion category C and embedding. And now we want this braid equivalence that identifies the bulk of the R and ZC to preserve this dual algebra. And more precisely, we take A beta. A beta is in ZR, and then there are two ways to get algebra in C. One is by forget and then embedding, and the other way is this equivalence and forget. We want them to be the same algebra in C. And you may notice here I put a quality here, which is not very natural in the context of higher categories, but there's some physical reason behind. So generally saying, we should allow some algebra as isomorphism or higher isomorphism here between the algebras. But for the symmetry, is kind of different. So this A beta, it is kind of the characterize the higher symmetry, and iota is embedding. So it is the macroscopic observable of the symmetry in the higher SED phase C. And if the difference, I mean the isomorphism here, if it is too non-trivial, and it leads to some observable results in the physical world, we would regard that these two things as kind of different symmetry. So for example, if you consider like a Z2 symmetry, and the two Z2 charges may mean different things physically. Maybe one is the rotation, and the other one is spin flip, and you cannot, although algebraically they are isomorphic group, but physically you cannot permute these two symmetries. So we really want some almost identity isomorphisms here. And of course, there are algebra isomorphisms that can be induced from higher structures such as natural isomorphisms, and we surely allow them. But after quotient out these things from higher structures, we would like this algebra isomorphism to be almost equality. But at the moment, it's hard for us to state this criterion in very precisely, because we don't really understand this higher structure very well. But remember that the thing is this algebra isomorphism should, at least for now, we don't regard as some additional data. Okay. So that basically completes our definition for higher symmetry and higher SED. There is immediately some applications or results or conjectures. So the first thing we can formulate the symmetry breaking in the higher SED phase. And the way we do it, just consider the push out in the category fusion categories. So we can push out and get a fusion category C0, and we also push out beta along this embedding. So it's easy to imagine that this push out of beta, this delta star beta, it describes the symmetry breaking in the higher SEDC, and the resulting C0 is some topological phase without the symmetry. And also we can describe this thing in terms of algebras. This push out of the beta is also a monumental functor, so it also canonically determines a commutative algebra in the center of C. And this algebra is basically the algebra A beta that embedded in C. And we can, in terms of this algebra, we can instead write our condition for the equivalence as that it preserves the algebras, the dual algebras in the bulk. So that's a symmetry breaking of the higher SED. And we can also consider the symmetry breaking in the bulk. And the basic idea is that the bulk or center is functorial based on the work of Kong, Wen, and Zheng. This functorial means you can not only take the center of R and V, you can also take the center of the morphism between them, and the morphism of morphism, and also higher morphism. But here we will only be interested in this beta. So we can take center of R, V, and beta as a bimodule between R and V, or domain wall between R and V. If we take the center of beta, the beta will be a domain wall in the bulk, and is actually a symmetry breaking domain wall. And the equivalence gamma we defined previously actually gives equivalence of the whole bulk. It is equivalence between these things, and these things. Great. Let me give you a few more details. So this ZR is ZR and ZV are just defined by the bimodule endo functors. And data we first translate into a bimodule, RV bimodule, by taking the same category as V, but with right action is the tensor product in V, and the left action is first apply this model functor beta and then tensor product in V. And the center of beta is just the bimodule RV bimodule functors of this special bimodule. And there are automatically some functors which are monoidal and central that maps from the bulk to the domain wall in the bulk. Also from ZV to Z beta. And this is special domain wall. It is monoidal bimodule. So to conclude, the bulk of our beta V is given by these data. The two bulks, the domain wall equipped with two monoidal central functors, and also similarly, you can construct these things for the SET phase on the other hand. And by saying that our gamma equivalence preserves the whole bulk, it just means we have in addition to gamma, we have a monoidal equivalence between the Z1 beta and Z1 of the beta pushed up beta. Also between the trivial center of the V and C0 of the symmetry broken bulk. And they commute with these central functors. And the idea is very straightforward, because this Z1 beta is just the modules over the dual algebra and also for the push out. So since we require that gamma preserves the algebras, it induces the equivalence between the categorical modules. And the gamma 0 is much easier, because you can see here that this functor is actually embedding, because we are taking a special bimodule. It's actually embedding, so gamma 0 is just a restriction of this gamma tilde. Okay, so that's the second application, the symmetry breaking of the bulk. And maybe the final thing I want to say is about the categorical gauging. So after realizing that we should use some equivalence functor of the bulk to describe the higher ST, and then we immediately get this picture of gauging. And what we really do is just put R, V together and glue them through their common bulk. But we do need this gamma functor as a intermediate. Intermediate is a transparent domain wall here. And we just put them together and we squeeze this sandwich. We got something in the same dimension as R and C. So this notation is just put them together in tensor product. And this R has a reverse, because the left hind and the left boundary and the right boundary have different orientations. And the result will be a fusion in category, and possibly multi-fusion in category, but we only know this examples in n equals to 1. So possibly this this gauging will be something unstable, but I conjecture that in higher dimensional it should always be stable. So it's basically this it's a new way of categorical gauging we are proposing in our paper. The resulting thing will be a topological phase without symmetry, and it should be the theory that after you gauge this higher symmetry R. And we can compare it to the old way of categorical gauging by either G-crossed extension or minimal modular extension. So our conjecture is that the the two ways should be equivalent. So for example, for this minimum model extension, that means R is rep G, or in rep G it's symmetric. And we conjecture if we do this categorical gauging glue along this gamma functor, it should produce a minimum module extension of C. Of course, add the looping to make them braided fusion -1 category. And moreover, we conjecture that this should be a bijection that's between this minimum extensions of a braided fusion in category and the equivalence functors that preserves. So in the symmetric case, just preserves embedding in the bulk of this in the bulk of the SED. Okay. I think this is already a very non-trivial conjecture. And that basically finished my talk. And I would like thanks to your attentions. And I left the last slides some open problems. And one thing is the higher structures I already mentioned. And maybe also we want to study the boundary theory of what have defined. There should be anomalous higher SDs and also maybe other exciting things. Yeah, thanks.
Thank you very much. You actually finished the talk before the time. Okay, so any questions?
Can I have a question? When you talk about this higher structure, higher symmetry, do you mean it's discrete higher symmetry, or you also include this continuous higher symmetry?
Well, since I define higher symmetry in terms of fusion categories, I think I will be limited to the finite things.